I'm going to tell you about relative velocity today. So I think technically it was in a previous lecture, but I didn't get around to it until now. So relative motion, let's say. So, you know, something that's been implicit from the start here is I've assumed that there's some sort of fixed frame of reference, right? There's some sort of origin, and somehow we have some way of measuring, how far you've gone over in the x direction at some point, how far in the y direction, how far in the z direction. I've never really explained to you how that's done, and yet you accept the reasonability. That word? Maybe not. Anyway, what?
Reasonableness.
Reasonableness. Seems like a reasonable enough thing, right? That you can find a point in three-dimensional space, and you can affix to it an x and y and a z coordinate, right? Now, that actually presupposes the existence of some sort of bijective correspondence between mathematical triples of real numbers and points in physical space, right? But that's so familiar to our everyday experience that you didn't really question it too much. But you should realize that I'm making a bold mathematical claim when I even suppose that such a thing can be done in physical space, right? In principle, you could make a distinction between physical geometry and a mathematical geometry of R3. And in fact, modern physics, we've learned that if you really take a hard look at things, that actually there isn't a correspondence perhaps between ordinary three-dimensional R3 and physical space. In fact, it's something probably more complicated. But to fully explain that would require us to discuss general relativity, and that's really a little bit above our pay grade at the moment. So it's a very good approximation, though, that points in space can be identified with, an x, y, z triple, right? But there's another thing you can do, right? You can start thinking about, okay, so I have one way of measuring where a point is, right? What if I have another way? What if there's somebody on a bicycle, and he says, no, I'm going to measure everything relative to where I am on this bicycle, and I'm going to measure x, y, and z relative to that bicycle moving, right? You could have a different so-called frame of reference. And then an interesting question becomes, how do you compare two different descriptions of motion, right? How do you compare the position, acceleration, the velocity relative to one frame of reference versus another frame of reference? That's what I want to talk about right now. So the basic thing is, we have two frames of reference, and I draw them two-dimensional. Well, I guess I can draw it three-dimensionally, why not? So here's one frame of reference. Let's say x, y, z, right? And then you could have another frame of reference, say z prime, y prime, x prime, right? And you could compare the description of the motion of a physical body relative to these two coordinate systems. So, let's suppose we're talking about a particle, and, it's traveling some path, whatever. And let's suppose it gets to right here, okay? So here's the particle. All right. Right there, and here is some indication of its path. I don't really care about its future or its, past path. I want to focus on a particular time t. Now, I'm going to make the assumption that there's a time t which makes sense for both coordinate systems. Okay? So there's some notion of universal time. I can talk about the same time for this one and that one, and we can synchronize our watches, and we can agree that time ticks on. But then I can also do, okay, so I have the position vector relative to the prime system. I could call r prime, not a derivative, but a notation. Okay, r prime. Or I could talk about the position vector relative to the unprimed system, just r, right? I can compare those position vectors, right? What I need then to make this puzzle complete is I need a description of the velocity, or excuse me, the position of the prime system with respect to the original system, right? So I need some name. Let's call this frame of reference S. let's call this frame of reference S prime. Again, a frame of reference is a somewhat complicated thing. It's an origin and a method of three rectilinear coordinates, meaning perpendicular directions, and I have some way of measuring distance from that origin at any given time. That's a kind of fantastically complicated thing, but oh well, we're going to use it. Now, here we have this guy right here, which we might call what? Maybe, I usually call it R sub naught. I mean, but what is R sub naught? Is the position of S prime's origin in S. All right? So what does this all do for us? Well, we know vector addition, right? And I do assume that there's some more fundamental backdrop of space, right, which you could look at either one of these things in terms of. So if you accept the existence of some such space, or I mean, anyway, take it or leave it. I think you guys will agree with me that we can write R is equal to what? R naught plus R prime, right? So, for example, if I have a system of coordinates on a train moving, right, and I set up an origin on the train, and I'm, say, 50 meters from the origin in the x direction on the train's x, right, and that train is at x equals to 100 relative to the ground, then the position on the position of that thing on the train would be 100 plus 50, it'd be at 150, because it's 50, you know, it's 100 to get where the train is, then it's another 50 on the train to get where that particle is. That's the equation of it. Oh, and then, okay, great, let me get to the point here. If you differentiate this, what do you get? Not too surprising, but let's think about what these things are. This, you might call the velocity, oh, come on, Parker. This is the velocity, oh, that's sad. There's a trash can in here, it's somewhere back there. Anyway, that marker can't waste our time again up here, that's the more important thing. Sorry if I hit you. Wasn't on purpose this time. Okay, so we could call this the velocity in the S frame. So you might call this v sub s, velocity relative to s, right? Well, it's equal to the velocity of the origin of the moving frame, let's say prime. Oh, by the way, just for the sake of discussion, let's think of s as being a fixed frame of reference, all right? That'll help us. So you got the velocity in the fixed frame of reference is equal to the velocity of the origin of the moving frame of reference plus the velocity of the particle relative to the moving frame of reference.
Velocity or the acceleration?
That's velocity, dr prime dt. R prime is not a derivative, it's just a label to say in the prime system. Okay. I would do R bar, but then I'd have R bar vector. And I once lost points over that, so I can't do it anymore. I don't know, who am I? I'm actually not joking. But you can't use that notation though. Just notation. Oh wait, anyway, I'll get over those points I lost at some point. So what happens, now getting to the acceleration though, differentiate again, right? So differentiate again, you've got d dvs, right, dt equals dv naught dt plus dvs prime dt. What does this tell us? This tells us that the acceleration in the S system is equal to the acceleration of the origin of the moving system plus the acceleration relative to the moving coordinate system. So let's see here. I think in all the problems I asked you about in mission 3, it is true that this is 0. This would be 0 for what are called inertially related frames. What are inertially related frames of reference? Two frames are inertially related if the one frame moves in a constant velocity motion with respect to the other one. So that would mean for particular material bodies that you're measuring the acceleration of, it means that the acceleration is the same whether you measure the acceleration with respect to the ground frame or with respect to the train frame, assuming that the train frame is moving at constant speed, right? The train goes around a turn, not going to do it. Changing direction, definitely not constant acceleration, you know. But all the problems that you're asked about are like that. Whether it's a river or a train, you're dealing with two frames of reference. One is moving at constant velocity with respect to the other. So, and pretty much all the questions that you're asked are really about addition of velocity, right? So, if you force yourself to sit down and identify what's the velocity I'm given, what's the velocity of the moving frame that I'm given, you'll be able to solve all of those problems basically just with this. The other thing that you need to know is, and this is kind of a jump I suppose, but for a train which is moving, gravity is the same on the train, right? The acceleration due to gravity on a moving train, and I think we've experienced this perhaps, you know, once you're moving and you're just on your merry way from here to Washington or whatever, you know, it's not like you feel lighter in your seat or something, right? Sitting in that seat feels the same as it does right now. Well, maybe those seats are more comfortable, I don't know. But, you know, gravity's the same on a train as it is on the ground. It's still 9.8 meters per second squared, you know, down. So, and that's it. I mean, it's the derivation of it anyway. Let me show you some specific problems, yeah? I have a few good examples that are, I think, more or less like the ones that you've been asked in WebAssign. So, get those. Any questions about this before I cover it up? We'll come back to this derivation again later when we talk about Newton's laws. That's after the first test. Your first test, which is when? Next Thursday or Friday, depending on who you are. So your first test is just mostly on, you know, vectors, obviously, and kinematics. Kinematics being study of motion. So Newton's laws, what are those? I don't know. Somebody said F equals ma or something, but we don't know about that yet. Eventually we'll learn, but not yet. Okay, so let's look at, this is lecture, I think it's lecture 5. I will eventually find it. Get out of this web viewer, it's no good. Oh, so I use bars in the notes. I hope you can deal with, I mean, bars or primes or stars if you like. I don't know. You can use x1, x2, and x3 for the first frame, and y1, y2, and y3 for the second frame, if you were so inclined. All right, so here's what I just went through. Here's an example. You throw a ball vertically, right, with speed v naught, and you're traveling in the northeast direction. Find the velocity of the ball relative to the ground. Right, so if you could somehow ignore that I was walking here and just look at that. I can't do it worth anything, but imagine that there was a train right behind a big row of bushes, if somebody was standing on the top of that train and threw a ball straight up relative to them, it wouldn't look like the ball was thrown straight up relative to you watching it on the ground, right? What you would see would be the ball going in some kind of like arcing motion, right? Because that ball also has the velocity of the train moving. So that's the basic. And so here's the math of that. The velocity of the train going in the northeast direction would be like 1 over root 2 I hat plus 1 over 2 root 2 j hat. That's a unit vector in the northeast direction. And so the velocity relative to the ground would be the velocity of the train plus the velocity of the ball relative to the train. But it's you know, what's happening to the ball relative to the train. It's one of these deals, right? I'm ignoring the wind blowing past it and everything like that. It just goes up and down, right? And how does it go up and down? U naught minus gt. That's it. So there you go. That would be the velocity relative to the ground. It's the velocity of the train plus the just ordinary up-down gravitational velocity. Another example, these river problems. Here you go. You have a river that has a speed of 0.55 meters per second. Now, that is, of course, relative to the Earth. Right? I'm saying it goes 0.55 meters per second, the water in it. It's a very boring river. All of the water is going in the same direction at the same speed. It's not like a real river, right? There's no turbulence or anything. Suppose the student swims up the river against the current, a distance of 1 kilometer. Whoa, that's pretty intense. Maybe it was, what's his name here, Steve? What's that? Steve what? Not Steven Seagal. Steven Seagal. Steven Seagal from which decade?
Oh.
Early 80s, okay, maybe. I don't think I could swim 10 meters up a river, but anyway, nor would I want to, who knows what's in the river. Anyway, a distance of 1 kilometer, and then he swims back to where he began. All right. If the student can swim at 1.1 meters per second in still water, then how long did he swim in the river? How long did swim in the river take? So there's two things going on here. The swim upriver, and there's a swim downriver, right, which was obviously faster. So when he's going upriver, so I'm analyzing this with respect to what frame of reference, the ground frame of reference, right? So when he's swimming upriver, the river is going this way, 0.55 meters per second. He's swimming relative to the river, 1.1 meters per second. So what's his effective speed relative to the ground when he's swimming upstream?
1.11 minus 0.55.
Right. So is it 1.11?
1.1, sorry.
1.1, oh yeah, 1.10 minus 0.55 meters per second. So this is the velocity relative to the ground while swimming upstream. Yeah, it's kind of a long label. I don't really recommend this label for your variable, but it is pretty descriptive.
I'll just write RTGWS.
There you go. But anyway, whatever that is, 0.55? Confusingly, it is 0.55. Sorry about that. Like, what a poor choice of numbers. Try to draw a distinction between the different numbers playing different roles. But it is true. His velocity upstream relative to the ground frame is 0.55 meters per second, right? So if he's going to swim a kilometer at that speed, then you take what? 1,000 meters divided by 0.55, and that tells you how much time it takes him to swim upstream a kilometer, right? Which is what? As it happens, 1,818.2 seconds.
That's a long time.
It is a pretty long time. What is that? 30 minutes? 30. And then his swim back downstream, on the other hand, is much easier because when he's going back down, when he's swimming with the current, relative to the to the Earth frame of reference, he gets the speed of the river plus the speed relative to the speed of the water, right? So effectively, he's booking it. He's 1.1 plus 0.55. He's going at 1.65 meters per second on his way back because he's going with the current. And so the 1,000 divided by 1.65, and I put minuses in here because I'm a slave to notation. Because if the change in x is positive upstream, it's negative downstream, but the velocity is also negative downstream. Okay. Anyway, if you use common sense to guide your math here, you can get away with not using the same. Let me shut up. So 606.1 seconds per done. So in total, about 40 minutes. Another popular problem. A car travels east at 30 kilometers per hour. All right, rain is falling and there's no wind. Suppose the raindrops make lines on the side windows of the car which have angles of 50 degrees with respect to the vertical. Now, I guess there's some cars that have vertical side windows, but I mean, actually, there are some, right? Almost vertical, but this is kind of rare. So I don't know, how would you have to adjust this analysis for like real car windows? I don't want to think about it. I mean, you could, but I would have to really sit and think about how to do this problem for real with a typical car with its curved windows and. That seems more like a job than an example for a lecture. Okay, so anyway, the lines on the side of the windows make 50 degrees with respect to this magical weirdo car with vertical sides. Okay, and I mean, if they're strictly vertical, the rain doesn't hit it either. Right? So, anyway, you see the spirit of the problem anyway, right? So, now of course, if the car is just sitting there and the rain is falling straight down, what angle does it make with respect to the vertical? 0, right? It's just falling straight with the vertical. Here it's making, if the car was going really, really fast, it would be like horizontal too, right? So somewhere in between that, that's. So here's the deal. The velocity of car is this, right? And so if you think about the velocity of the rain in the car frame, what's the velocity of the rain in the car frame is in part of the question. So I give it a label because I don't know it to start with. I say it's a plus a hat, a plus ai hat plus bj hat. All right, that goes in the direction of the traces on the car anyway. Agree? So like if you're going along in the car and you see that, the rain looks like it goes like this on the window, that is indicative of the velocity of the rain in the car frame. You agree? Okay, so that's one of my thoughts. So thinking of the car frame like S bar or S prime, and the ground is S, so I've got that the velocity in the ground is equal to the velocity of the car, whatever that is, plus the velocity of the rain relative to the car frame. Right? So what does that say? That actually says that the velocity of the rain is equal to the velocity of the car. Oh, okay, so I'm sorry. This was a general statement for arbitrary velocities. I'm just saying that also applies to the rain. Sorry, I was getting ahead of myself. I was saying that this equation is that equation. The idea is that this is the equation in general, so it applies to the case of the rain. Okay? You're like, well, you didn't need to write that. Fine. I guess I didn't need to write that. Got it. Okay, so getting to the point. So what we have here is the velocity of the rain with respect to the ground we're given falling straight down. So it's minus v naught j hat. Right? And we're ignoring acceleration of the rain, by the way. Right? It's kind of funny. Right? Rain falls down. Why isn't it accelerating? I mean, if you think about it, is it kind of terrifying if clouds rain from like 10 miles up? Wouldn't that really hurt?
Well, terminal velocity.
Ah, terminal velocity. What's that?
When air resistance basically gets to stop accelerating.
Air resistance.
We're ignoring it.
We're ignoring air resistance, right? So here I'm
That's the scary world. We should figure out how high the cloud would have.
how high would it cloud have if you didn't kill somebody?
It's so high of a tail.
Yeah, as long as it hits terminal velocity, it's never gonna
Is
kill
this person a witch? So let's think about what you're going on.
If you put a bullet in there, then
A cloud of bullets. You guys have all kinds of ideas. Price lead clouds. You don't want to be around with that precipitates, it's true. But, okay, so getting back to my story here, we have the velocity of the rain relative to the ground frame, the velocity of the car, right? And then the thing we don't know. But this is a vector equation, so you can equate the x direction and the y direction separately, right? So x direction must be this, right? So that means the a has to be minus 30, and b has to be minus v naught, right? All right, but what else do we know? We know that, we know the angle, right? So, where's this minus 140 coming from?
50 degrees.
Yeah, the vertical. 50 degrees minus 180, right? So anyway, that gives me then, from the A and the B, so I know A and B, and I know the angle is minus 140 when I draw the right picture. Where would it go? It's not the right picture. Sorry, I think I've covered the picture up there. But then I can then figure out what the velocity had to be because, you know, I know the angle. I don't know V naught yet, but when I put these things together, I do. So, let's see, in miles per hour, you'd have a speed of 18.65 miles per hour. Implies rain falling at 115.6 miles per hour. I don't know what are good, realistic speeds for rainfall, honestly. Yeah.
You said the negative 140 is coming from 50 off the vertical minus 180.
Yeah.
that's,
But isn't that negative 130?
Oh, have I done it wrong?
No, it's 90 degrees over, or it's 50 degrees over vertical, which could add to it. Bring it around.
50 degrees from the vertical.
I probably should have 130 there.
Yeah.
Almost, yeah.
I'm
I have to reskin that.
You just draw 6 over the 5 and call it a day.
Sorry,
No,
guys.
sorry. Go over the 5.
Apparently I don't know that 180 degrees, you know, that's a line. Sorry, for some reason 190 minus 50. I don't know what am I doing. Okay, the idea of the problem is right? But obviously that should be 130, not.
No, that is correct because you've got negative 90 plus negative 50.
Oh, I do? Oh, so it's not 180. Oh, yeah, the picture. I'm sorry.
Where's the picture?
So you guys agree with it? Right.
We should take a break.
Now we gotta think about it. So I was given 50 degrees with respect to the vertical like that, right? So, oh, I see. So it's going down that way. So that's 90 degrees plus 50. That's 140 degrees clockwise, which is minus 140. Oh,
That makes sense.
I know. I just mathematically wanted to believe I should take 180 minus 50, but I had no reason for doing that. It was just me speculating. Should pay attention to my notes. Sorry. Duh. Okay. Yes?
Can you explain the two conditions part?
The two conditions?
This gives us two conditions.
Right, so I have a vector equation. I have j hat and I hat, right? These are in totally different directions. So if you have a two-dimensional vector equation, you get the x component equals the x component, and you get the y component equals the y component. Those are the two conditions. There's no x component over here, right? So it must be that the sum of the x components, which are 30 and a, so 30 plus a must be 0. So a must be minus 30 kilometers per hour. And on the other hand, the j hat components have to match too, right? So that's why b has to be minus v naught. But of course, another person might have worked this problem and just immediately seen intuitively that the rain was falling in this direction relative to the car. You know, like if the car is going this way, then the rain's going that way, which would be in that sort of, what's the word? Third quadrant direction relative to the car frame. Somebody else might have worked this problem without going and inventing this A and B. They might just see it and write it down. But for those of us who don't see it, I think it's helpful to invent some math and explain it from base principles as much as I can. Here's another one. An airline pilot makes a heading due west by his GPS locator. So that would mean due west relative to the frame of the Earth. Right? And the plane has an airspeed of 140 kilometers per hour. All right? That's his speed relative to the air. That might not be his speed relative to the ground. Right? Maybe you heard in the news there was some like stupidly high tailwinds, people like chopping an hour off their transit from Europe to the US last week. Because they're riding on, and they were like going so fast that they were almost going the speed of sound relative to the ground. They were like, 500 miles airspeed plus like a 200 mile an hour wind or whatever. I'm not kidding. Like, it's true. If you travel internationally, you'll be like half hour or an hour sometimes, either off your flight time just on the basis of winds that you're traveling with the jet stream and stuff. It's a significant effect. Anyway, so if there's a north wind of 27 kilometers per hour, find the velocity of the airplane relative to the ground. All right, so define my terms. Velocity of the plane relative to the ground is equal to the velocity of the wind, which is the moving frame of reference on which the plane is going. All right? And the velocity of the plane relative to the wind, that's given by the airspeed. Okay. So what do I know? I know that the pilot notes, according to his GPS readings, that they are going in the western direction, which means that their net speed, whatever it is, we don't know it at the start, but we do know its direction. It's the minus I hat direction. It's west. Okay. And then the velocity of the wind. Well, I'm given that the wind is 27 kilometers per hour north. So that's why I'm able to say velocity of the wind, 27.0 kilometers per hour J hat. It's north. And then plus A hat I plus B hat Bj. I don't know the airspeed. I know the airspeed. I don't know its direction. Right? I don't know the direction of the plane relative to the wind in the given. What's given? It's not given to me. So I know that there's some vector I can add here. I know that its magnitude is 140 kilometers per hour, but that's it, right? But that's okay. I can solve that because it's two equations and two unknowns. Again, I can match the x and the y directions and see what it gives me. So like, apparently, minus v naught is a, comparing I hats. And, well, there's no j hat over here, right? So the sum of the y components over here must be 0, which gives me what? B is minus 27.0 kilometers per hour, right? Oh, but check that out. Once I know B, I can go back up here and I can figure out what A hat would be, right? See this? I know B from here. Then I can take that number, plug it back up in here, and solve for A. Plus or minus A, right? I can use some common sense to figure out whether A is positive or negative, right? So here's that math. I go plug this 27 into the speed equation. Out pops 142.6 kilometers per hour. Really plus or minus that, right? Well, I guess I take the positive number because it's a speed. Duh. So anyway, the velocity of the plane relative to the ground is in fact minus 142.6 kilometers per hour. And if I wanted to, I could go back and now figure out what is the direction of the plane relative to the wind also. If I wanted to, I could go back and figure that out too, but I wasn't asked it, so I didn't bother. Yep.
So are we assuming here that the plane is heading west regardless of the wind resistance?
Yes, that's given to us by our headings.
But the GPS is gonna tell them which direction it goes west. He'll point in that direction and the wind will change its course, right?
No. I'm telling you, the GPS tells you you're going west. Where the plane is pointed, well, I don't know, I haven't figured that out.
Oh, okay, so that's irrelevant.
But it's not pointed west.
Okay.
Right, I mean, it's, if the wind is pointing north, if the wind's blowing north, and you're actually traveling west.
Southwest.
Yeah, you have to be like south a little bit, yeah. Yep.
So negative V naught I have above that curly brace.
Yep, where'd that come from?
Yeah. What is that?
So the reason that we have this, that's the velocity of the plane relative to the ground. I was given this problem that the GPS locator said that the heading was due west. So west is the minus x direction in our standard setup, so that's why I'm doing the minus. And the V naught is the speed, it's the positive magnitude of the velocity. These problems drive me nuts. The wording, sometimes I really have trouble making sense of which one is what they're saying. So I will try to, if I was to ask this question on a test, I will try to use wording that is very similar to this. Because I don't want you confused about what the wording means. I want you to actually be able to solve the physics problem without knowing a bunch of airline lingo. No, not really the point in here. Let's see here. Oh, mathematical errors recurve. So have a nice weekend, guys. We're done. Only 14 minutes, really.